Ever wondered how AI crafts lifelike images, music, or even text without explicit rules? The answer lies in implicit generative models, systems that learn patterns from data and generate new examples by transforming noise into meaning. But training these models, it's like painting a masterpiece with a brush that keeps slipping. Today, we're diving into a breakthrough called Dual-ISL that's revolutionizing this process. Let's unpack how it works and why it matters. Implicit models like GANs don't try to map every detail of real data. Instead, they take random noise and turn it into something meaningful. Think of it as turning static into a photo of a cat. But here's the catch. Training them is notoriously tricky. They often get stuck in loops, produce repetitive outputs, or fail to capture complex patterns. This is where invariant statistical loss, ISL, steps in. ISL is a clever technique that compares data by their ranks. Imagine sorting data points and checking if the model's output matches the real data's order. It's like grading a student not by their exact answers, but by how well their responses align with the correct sequence. But here's the twist. Researchers flipped the script. They swapped real data and model outputs in ISL, creating Dual-ISL. Why does this matter? Because it unlocks convexity, a smooth, predictable path to the best solution. Imagine climbing a hill with no dips or plateaus. Classical methods like KL divergence or Wasserstein distances can get stuck in tricky terrain, but Dual-ISL ensures a clear route to the top. The math behind this. It involves Bernstein polynomials, a tool for approximating functions, like building a bridge between the model's output and real data. By projecting the density ratio, how the model differs from reality, onto these polynomials, researchers get exact error bounds and guaranteed convergence rates. It's like having a roadmap with mile markers for every step of the journey. And here's the kicker. Dual-ISL doesn't just improve training, it gives an explicit density approximation. Most implicit models hide their internal probabilities, but this method makes them visible. It's like revealing the recipe behind a secret sauce, letting us diagnose issues and refine models more effectively. In experiments, Dual-ISL outperformed traditional methods. It converged faster, avoided mode collapse, where models repeat the same output, and captured tricky patterns like heavy-tailed distributions. Think of it as upgrading from a shaky skateboard to a rocket ship for training AI. So how does Dual-ISL work? Let's break it down. First, it defines a ratio, Qx equals Px/Pex. This ratio tells us how our target distribution Px compares to a simpler 1Pex at every point. But integrating this directly is tricky. Here's the clever part. We change variables using T equals Fex, where Fex is the cumulative distribution of our simpler model. This transforms the problem into a uniform square domain, like stretching a complex shape into something simple and manageable. Now, the integral becomes something we can handle with Bernstein polynomials. These are like building blocks for approximating functions. They're smooth, flexible, and guaranteed to work for continuous functions. But here's the twist. Dual-ISL doesn't just use the polynomials themselves. It also uses their dual counterparts, special weights that make the approximation super precise. The math involves a Gram matrix, a way to organize relationships between these polynomials. By solving a system of equations using that dual basis, we find coefficients that let us reconstruct Qx with incredible precision. And as we increase the number of terms, k, the approximation gets better and better, converging uniformly to the true function. But why does this matter? Let's look at the results. In experiments, Dual-ISL outperformed classical methods by a mile. When modeling tricky distributions like the Cauchy or Pareto, it captured the data's quirks far better. On 2D datasets like the dual moon, two separate clusters or two rings, concentric circles, it preserved the exact structure without merging disconnected regions, a common issue with other models. And it's not just about accuracy, it's about faithfully capturing the structure of the data. Traditional methods might match averages or densities, but Dual-ISL gets the whole story. Plus, it's faster. Benchmark tests showed it outperformed classical ISL in speed while maintaining precision. So what's the takeaway? Dual-ISL is a game changer for AI and data science. By combining clever math with practical tools, it's making it easier to model complex real-world data. Whether you're generating images, predicting stock prices, or analyzing medical data, this technique is paving the way for more reliable, efficient AI. The next time you see an AI-created masterpiece, remember, behind the magic is a revolution in how we train these models. Thanks for watching, stay curious, and keep exploring the frontier of machine learning.